The objective of this video is to practice doing winding factor calculations by analyzing the base winding. And this video does not introduce any new content. However, I think that you will find following along with this example very useful because we're going to be considering a winding which consists of multiple base windings, and we'll then show how we can analyze a single base winding to determine our complete winding factors, including the subharmonics. And by analyzing the base winding, we can save ourselves a lot of effort, especially for windings that have a relatively short base winding compared to the overall winding length. And the specific example that we're going to be considering in this video is a 24-slot, 20-pole motor with 3 phases wound with a double-layer concentrated winding. So this is a fractional slot concentrated winding. And my first question to you is, what harmonics can be present in this winding? Look at the properties of the winding and see if you can tell me which harmonics can be present. Give it a try on your own, and when you're ready to watch me do it, press play. So for this winding, we can write Q as being 2 divided by 5. So therefore, little n is an odd number, which means it's a first grade winding, and therefore the number of pole pairs in our base winding is going to be 5. The harmonics are going to be at V equals 1 by P star. So V can be 1 over 5, 2 over 5, 3 over 5, 4 over 5, 1, 1, and 1 over 5, and so on. Now, what's interesting is that we can also talk about this harmonics in terms of the harmonic index of our mechanical radians. So remember, V is the harmonic index of our number of pole pairs, whereas N is the harmonic index of one revolution around our stator. And so if you recall, N is equal to V times P, and since P is 10, N is equal to 10 times V. And so we can write out and match that V equal to 1 over 5 is equal to N of 2. V of 4 over 5 is equal to N of 8, and so on. Next, I want you to draw the star of slots to lay out the top winding layer. And then I want you to compare the star of slots to the star of slots of the base winding of this winding. So first, do the normal design steps, lay out the top winding layer by using the star of slots, and then compare that star of slots to the star of slots you draw for the base winding. Go ahead, give it a try, and resume watching the video when you're ready to watch me do it. So I've now got the star of slots for our full winding, and you can see that I've labeled the first layer of the star of slots in black, and I've put brown labels for the second layer. And then I've assigned the coil sides, so phase U in the positive direction belongs to coil sides 1, 6, 13, and 18 in the top layer, whereas phase U in the negative direction belongs to coil sides 7, 12, 19, and 24. And now we can compare this to the base winding. And so to study the base winding, we're studying a winding of equivalent machine that has Q prime slots and P prime poles. And so what we see when we analyze a base winding is that we get the same spacing between phasors, and we have the same number of phasors within the layer. So one layer of the star of slots has 12 phasors. The base winding will have the same number of phasors as our full winding did. The only difference between the star of slots of the base winding and the star of the slots of the full winding is that the base winding consists of a single layer instead of 2 layers. So if you just take this diagram right here and you remove the brown labels, you will have the base winding diagram. Next, I want you to propose the coil pitch for this. And this is a little bit arbitrary or trivial, I should say, because I've already told you it's a concentrated winding. So please go ahead and do this or watch me do it. So we can see a full pitch coil would be 6/5 of a slot, and so we'll round this down and obtain a pitch of 1 slot. Next, I want you to construct a table of winding factor magnitudes that compare the full winding and the base winding. You can give this a try on your own if you want, but I suggest that you watch me do it to see the approach that I take. And so we're going to do this by calculating winding factors from a pitch factor and a distribution factor, where we've noted in a previous video their definition. And we calculated the pitch factor and distribution factor based on these expressions here, where alpha I is the location of each coil side in the top layer belonging to a phase winding. And so we'll do this, we'll evaluate these expressions for both the full winding and the base winding. And so I'm writing this out as a sum of exponentials that I'll take the absolute value of. And I'm doing this based on our star of slots assignment for phase U. And so you can see I've got our first coil side right here. Our second coil side is in slot 6, and that's going to be at an angle of slot 6 minus 1 times alpha C. So alpha C is the angle between adjacent slots in our stator, and this slot is 5 slots away. Its slot index is 6, so 6 minus 1 is 5 slots away, and we'll multiply that by alpha C to get the angular location of it. So I'm writing it this way to provide more physical meaning for the long expression I'm about to write out. And so when you look at this expression, you can see that we've got slot 6, slot 7, 12, 13, 18, 19, 24. And again, that indeed matches our labels up here, our assignment to the phase U zones. And then we indicate positive and negative by adding or subtracting these individual phasors. So all of this, the sign and the slot number, matches this diagram up here. Okay, so those are our expressions for the 24 slot full winding. Now let's write out a set of expressions for the base winding. And remember, the base winding, we consider it as being an equivalent machine with Q star slots and P star poles. And we've already determined the assignment of the coil size as just being the first layer of this. So we just have 4 coils instead of 8. And in fact, we notice that the first 4 terms of this expression are identical to this expression of our base winding. The only difference is that now alpha C is equal to pi by 6 instead of pi by 12. So we'll go ahead and evaluate this in the form of a table. So if you evaluate these expressions up here that we've established and use that to calculate the winding factor by using this, you get the following values that I've already loaded in this table. So starting with V equals 1/5, remember this was the lowest order harmonic that we expected to find in our winding from up here. So we wrote out this table for these values of V, and then so here you can see these are the values of V, and then moving left to right, we calculated what N is for those values of a winding. So for our 24 slot winding, N was 2, 4, 6, 8, and that matched this up here. And then for our base winding, an equivalent machine with our base winding, we would have N equals 1, 2, 3, 4, 5, 6. And so we plugged in these values for V into our expressions up here, and we get out these winding factors. So you notice that the winding factors are the same for our 2 windings, which is what we expected, so that's nice. And this means that we could use our base winding to get the winding factors for our complete winding, which we would prefer to do because if you notice, the base winding is half the number of coils. this expression is much easier to work with than this expression. But there's something interesting here. Remember that we've said that our harmonic content is only going to be the 1/5, 2/5, and 3/5 harmonics, yet we can see that our full winding actually can have values of n equal 1, 2, 3, 4, 5. So these values I'm labeling in red are harmonics that our predictions say should not exist. And there's nothing that stops you from plugging in those values of n into this expression up here, right? Because we can map this, can go over here to this harmonic as 1/10, 3/10, and so on. And if you plug those in, you will find that you get 0 winding factor at those harmonics, which is what our calculations anticipated up here in part A. That is what we expected based on this analysis. And what's interesting is that these harmonics simply don't exist in our base winding, right? There's no way that we can have n equals, we can have a harmonic for V equal to 1/10 in our base winding, because that would require 2 revolutions around our stator, which does not make sense. And so you can see that because our base winding is our shortest independent segment of winding, any harmonics that can't exist in the base winding simply won't exist in our full winding either. So this example gives you a way this example shows you how you can use your base winding to make calculations of the winding factor for your complete winding. And this is useful, again, because the base winding spans multiple combinations of slots and poles. So it's any time that you have the same value of Q, lowercase q, slots per pole per phase, you're going to have the same base winding. That means that you could be considering designing a winding that is 24 slots with 10 poles, or a winding with 12 slots and 5 poles, and you're going to end up having the same base winding and the same winding factors. In summary, this video has practiced an example where we considered a winding which was composed of multiple base windings, and then we showed the equivalency of studying the base winding versus studying the full winding. And the final conclusion is that we're able to calculate all the winding factor information that we need by simply studying the base winding. And in very high slot number machines, this is a tremendous time-saving tool.